In this example, you should see that something is very different from our last example. You notice these are not evenly spaced. 0 to 1, that's 1. 1 to 3 is 2. 3 to 6, 3. 0.6 here, 1.4, and 2. So we're not going to be able to write that shortcut where we factored out the 1/2, for example, in the last problem. All right, let's just try this. Approximate this integral from 1 to 8 of f of x dx. A lot of people just start crunching numbers. Let's look at it. We want to start at 1, so we don't care about this. And we're only going to 8, so we don't care about this either. All right, so we're going to approximate this. Let's start with left. How many can we have? Well, we can have 1, 2, 3, 4. Okay, so our first one is 2 units wide. And we're going to use the height of the left side. Okay, the next one is 3 units wide, and the height is 3. Then it's 6/10 units wide, 1 unit tall, and then 1.4 units wide and 5 units tall. All right, now if I did that correctly, I think I get 22.6. Let's try another way. We're going to approximate it this time using right-hand rectangles. Same thing, we get 4. I clear this out. Okay. So our first one again is still 2 wide, but this time is 3 tall. And the same as the last one, but this is different. 3 wide and only 1 tall. 6/10 wide, 5 tall, and then 1.4 wide, but 8 tall. So this one's a bit bigger, 23.2. And I'd like to use a trapezoid because I like that this is not equal parts here. So again, we're going to have 4. So we're going to have 1/2 times the height, which is 2, and the bases, which are 3 and 3. Then we're going to have 1/2 times 3, and the bases are 3 and 1. So we can't use that shortcut in writing it out. Plus 1/2, 6/10, and 1 plus 5. And then the last one plus 1/2 times 1.4 times 5 plus 8. All right. So you could factor out the 1/2 if you wanted. Oh, I think that equals 22.9 if I added that correctly. Okay, but it's good to show where these numbers are coming from. Don't just write 1 or just ignore it. Don't just write 3/2. Show where your numbers are coming from. It's a really good habit to get into. Now, we noticed that it said f is a continuous function for all x. Could any of these approximations represent the approximate areas of the region? Honestly, we don't know. We don't know if f is non-negative, so we can't determine if they do represent the area. All right, and then the last part, we're going to approximate f prime of 7. And the only way we can do that is by looking in between those two values. So we're going to have 8 minus 5 over 8 minus 6.6. So I believe that that is 15 over 7. Okay, so now we're going to look at properties of integrals here. And you can read through this, but I'm going to explain some of the newer ones in the bottom here. Now that's pretty messy, so we're going to try to write it a little bit differently. So there's a way we can break it up. Oops. And we could break it up like this. Okay, but not only can we do that, we can also move that 3 right out into the front. Okay, this is going to be helpful in a minute. We're going to use that information we already had. We know that from 0 to 10 is 8, and 0 to 8, or 0 to 10 is 17, and 0 to 8 is 12. We need to get from 8 to 10. Okay, so to do that, we we have to find a way to combine these two. All right, and I think the easiest way, let's go like this. Let's say negative 8. No, that's not what I meant. I meant negative 8 to 0 f of x dx plus 0 to 10. Now if I go from 8 to 0 and then 0 to 10, I'm combining that. I can then connect from 8 to 10 f of x dx. That would be the same as 8 to 10 of f of x dx. So if I have negative, oh, actually, I don't really want that negative in there. Sorry about that. What I was thinking is I'm going to have to take the opposite of what this is. So if 0 to 8 is 12, then 8 to 0 is negative 12. 0 to 10 is 17. So that means that this part of the integral is equal to 5. So if we plug that back into our original, we have 3 times 5 plus, all right, and let's look at this graphically. Here's our equation, y equals 2, and we're going to do from 8 to 10. So it's a height of 2 and a width of 2, so this is 4 plus 4, this is equal to 19. Okay? Let's try to break apart, let's see, we're trying to find this. We're going to break it up a little bit. I could pull that 1/2 out into the front. I can separate it and have an integral from negative 6 to 3 of 3. And notice I put the negative on the outside. That's what we need to solve. So in order to do that, we need this integral. We don't have it yet. Okay, so, but we can find it using the information that we have. So I need negative 6 to 3. Well, I got 7 and 7 on these, so there's probably a way I can combine that. All right, let's go. We'll keep this one the same, 4 to 7. And if I could add the integral from 7 to 3, that would give me the integral from 4 to 3. Not quite good enough, but we'll get there eventually. So 4 to 7 is 5. 3 to 7 is 9. So 7 to 3 is negative 9. So this integral is equal to negative 4. Okay, and we can build on that. And we know that from negative 6 to 4, or 4 to negative 6, so we could find negative 6 to 4. Negative 6 to 4, plus 4 to 3, that's going to give us the integral we want from negative 6 to 3. So if 4 to negative 6 is negative 3, negative 6 to 4 is positive 3. 4 to 3 is negative 4. So this is equal to negative 1. Going back to our original problem, so 1/2 times negative 1 minus, and now this is just a rectangle with a height of 3 and a width of 9, and I got that because it's negative 6 to 3. So we have what, negative 1/2 minus 27, or 54 halves, so negative 55 halves. Not bad. At the very end, we're going to look at this function, and you notice the upper limit is missing, so I'll add that in there, 0 to pi. The integral from 0 to pi of sine of x dx is equal to 2. We're going to use that and symmetry. We're going to use symmetry here to find the following. I don't know why some of these didn't print. Okay, so pi, it looks like pi didn't print on any of these. So from pi to 2 pi, think about this graph. If we continue this on, from pi to 2 pi is going to have the same area of 2, but it's below the x-axis. So that's going to be negative 2. This time we're going to go from 0 to 2 pi. Okay, so if we go from 0 all the way to 2 pi, the first part has a positive 2 area. The second part has a 2 area, but it's below the x-axis, so they cancel each other out. Be 0. This one's going from pi to pi over 2. Okay, pi is here. Pi over 2 is here. So we're going from here to here. If that whole area is 2, this area is 1. We're going backwards, so this is going to be -1. The next one's going from 0 to pi of 2 plus sine of x. So you got to think about what that would do for our function. If we have 2 plus sine of x, we're just raising this graph up 2 units. So we're just going to add this rectangle here. So the area of that rectangle is going to be 2 times pi. So we're going to have 2 pi plus our original 2. Okay, the next one's going from 0 to pi of 2 sine of x. Think about what that 2 would do to the function. Instead of going up to 1, now it's going to go up to 2. So we're going to double our area there. Instead of having an area of 2, we'll have an area of 4. All right, this one, it says 2 to pi plus 2. All right, it was 0 to pi. We just added 2 to each of those. We moved it to the right. And this tells me we moved our function to the right. So that's going to conserve that same amount of area. It's just 2. This one's going 0 to 2 pi. But what changed? The period on this changed. So the new period of that would be 4 pi. So if we look at that graph, how that's going to change it, instead of going half there, it's going to go half at 2 pi. So it's going to double the area. So instead of being 2, it'll be 4. Oh, sorry, wrong one. 4. This is negative 1/2 pi to pi. Okay, if you look at the graph, negative 1/2, or negative pi to positive pi, these areas cancel out. 0. All right, and these last ones are for you. We're going from 0 to pi, but this time with cosine. Think about what the graph of cosine is. And 0 to 2 pi for cosine. Think about the graph and answer those.